The Bellman-Ford algorithm for finding shortest path from a single source to all other vertices in a graph is a general solution to the single source shortest path problem. It's a remarkably simple algorithm, and it also allows the weights to be negative. So if a graph has negative weights, Bellman-Ford algorithm runs fine if there is a shortest path. And if there is a negative weight cycle in a graph, then Bellman-Ford algorithm can even detect that. So the idea behind Bellman-Ford algorithm is pretty straightforward. For each vertex in my graph, and for each vertex that I pick, for each edge that's associated with this vertex, I just keep relaxing the edges. Now, after all edges have been relaxed, we check for negative weight cycle, and if for any edge uv we see that v dot d is more than u dot d plus the weight that connects u to v, then we have detected a negative weight cycle, and then we return false. That is, we Bellman-Ford failed to find optimal solution because there's a negative weight cycle. The Dijkstra's algorithm for finding shortest path between a source vertex and all other vertices in a graph works only when the edge weights are non-negative. So if any of the weights in the graph were negative, then Dijkstra's algorithm fails to find the shortest path from the starting vertex to all the vertices in the graph. The algorithm once again begins by running the initialized single source method, where we set all the d and v, d and pi to the respective values, d to infinite and your pi to nil. The algorithm maintains a set of vertices S whose final shortest path weights from the starting node S have already been determined. So this is in a way this is a maintain of the solution. The overall algorithm behaves in a way like a combination of the Prim's algorithm and the breadth first search algorithm. So in Prim's algorithm, if you remember, what we do is we pick the item with the minimum value using a priority queue, and BFS in a way explores all of its breadths first. We include all the vertices into a queue, and then we extract minimum from the queue based on the current distance estimate. So since the initialized single source initially sets the distance value of the source node as 0, this is the first item that will be extracted from the queue, and it will be added as a solution, and we continue this. So and then after that we select each vertex adjacent to the current vertex that we pulled out from the queue, and then we relax that. So you can see that after we have started from a source vertex, we explore all possible options, and then we pick the option that has the minimum, that gives you the minimum path, and then say after we picked it, we look at all possible options for that path, and then once again we pick the next node based on the minimum shortest path estimate for that, and then we repeat it until we visited all the items in the priority queue. Now the running time for Dijkstra's algorithm is big O of v times the time needed for extract min plus e, and this is e because we run this relax operation for total number of edges in the graph. One interesting feature of the Dijkstra's algorithm is that it can run fine in a graph that has cycles like this, but it cannot be run successfully on a graph that has negative weights.